In this video, we are going to go over the first algorithm for computing the minimum spanning tree, which is the Prim's algorithm. There are several hundreds of algorithms that are used to calculate the minimum spanning tree, but for the sake of the course, we'll just discuss two of them which are most popularly used. The first one is Prim's that we are going to discuss now, and the next one is Kruskal's that we are going to discuss in the next video. So the Prim's algorithm analyzes all the connections between vertices and finds the set with the total minimum weight that makes the graph connected. So the vertices are divided into two sets when we are trying to compute the MST in this algorithm. It works pretty similar to what we saw in the Dijkstra's shortest path algorithm, where we have like two different sets. Set S will keep a track of vertices in the minimum spanning tree or whatever we have already computed. Initially, this is going to be empty, and V minus S is going to be all the vertices we have which we have not processed yet. So in this case, initially all of this vertices in this graph, which is from 0 to 5, will be a part of V minus S. Next, what we do is we choose the edge which connects with the smallest weight in set S to a vertex in set V minus S. So what we are going to do is we are going to arbitrarily cut the graph into two different components. The first one will be all the vertices in the set V, and the other one will be all the vertices in set V minus S. Next, we are going to see what are the edges that connect these two sets. So let's look at it in more cleaner way. So let's say if 1 and 0 are in the set, then 2, 3, 4, 5 are in V minus S. We have four choices that we can make, which is this, and this. Now, out of all these four, the number 1, the weight 1, the edge with weight 1, which is 0, 2, has the least cost. So what we are going to do is we are going to add this 0, 2 to our minimum spanning tree. Like that edge will surely be in the minimum spanning tree. And we are going to mark these two 0 as in 2's, which is we are going to bring this vertex which we have chosen from V minus S to this new set. So after that, our new set would look something like this, which is after our choice, our new set would look something like this, which is now our cut will be something like this. This is one set and this one is another. We are going to see a worked example soon, and you're going to realize that how this works. But typically, we just do this till all the vertices have been computed or V minus S is equal to null. Like it is an empty set. Now, why we are doing this is because all these different graph algorithms that compute MST are based on a property called cut in mathematics. So what is a cut? So a cut is basically a arbitrary distinction of two different sets, which is if you choose some vertices that are present in your graph, you can move a certain set, or you can cut the graph into two different components such that one set is on one side and another set is on another side. Now, the property of cut says that if we make any arbitrary cut, which is not just this one, any arbitrary cut, like if we place some vertices in one set and another one in another, all the edges that connect these two different sets, like if we have the set V and V minus S, the minimum one will always be a part of minimum spanning tree. So we are not discussing the proof of this cut property. It is very simple. Like if you are curious to know, just search the web and you'll understand that. But typically all these cut properties and this explanation is in the grad level course. But underlying all these algorithms, the idea is that we make arbitrary cuts, and at every cut like we make, we choose the minimum edge And that is always a part of MST, because that's there's some mathematics behind it, because if we did not had that, it will lead to a cycle. And you can prove that, like, if you're interested. So let's see a worked example of the Prim's algorithm. Here we have V that is empty initially, and V minus S that has all the vertices. So we'll start the Prim's algorithm by taking into account just one vertex, which is, we can have any arbitrary vertex. We can also pass in the source. So in this case, like, let's say I'm passing 0 as an arbitrary vertex. Now, one thing you have to note is that the minimum spanning tree algorithm, like Prim's, will give you unique MSTs if the weights are unique. If they are similar weights, like if there are more than one non-unique weights, it will give you the minimum spanning tree, but it could be non-unique, which is, it could be there could be multiple MSTs that are possible. So initially we move 0 to V, and we remove 0 from this V minus S set. Now what we are going to see is what are the edges that connect 0 or this set V with this set V minus S. So we are making a cut right here. So we have just three vertices that are possible, which is this, this, and this. And now we'll choose one, since that's the minimum. So we choose the edge that has weight 1, because that is the minimum out of all three that are available. So in this case, 0 and 2 will always be the part of MST, which is, we have these three choices. We pick 0, 2. Now, since 2 is the connecting edge, the new connecting edge, we move that to the set V minus S, from V minus S to V. So 2 will be deleted. So as you can see, now we have 0, 2 in V and 1, 3, 4, 5 in the V minus S. So typically the algorithm is working in a manner such that we need to visit each vertex exactly once, which is, in V minus S, we are taking one vertex at a time and performing some computation. Next, we have these two sets. So now our cut will look something like this, which is, this is one cut and the other ones are in another set. So we'll see what are the edges that connect 0 and 2 to all other parts of the graph. So a way to look at this is to see which are the edges that connect 0 and 2 to every other vertex. So we have one possibility is this is another one, this is another one, this, uh, this, this, and this. The remaining ones are not connected to either 0 or 1. Now this one is already a part of MST, so we don't care. Another thing we don't care is those edges that are within this set. So if they are not connecting each other, like right now, you are not going to see an example of this, but in the next one, you're going to see, in the next iteration, you are going to see an example of which of the edges to ignore. So we have all these possibilities. We'll see which of these is the minimum. So in this case, this number 4 seems to be the minimum, which means 2 and 5 has the minimum cost associated with it, because we have already finished processing 0 and 2, and that's a part of the minimum spanning tree. So we are going to again, like, move 5 to this vertex and choose this 2, 5 that will be a part of our MST algorithm, or the final output. Okay, so we have now 0, 2, and 5 as one of the two edges of the uh, entire MST, or the final output. Next, we'll see what are the edges that connect 0, 2, and 3, and 5. So in this case, we have all these ones available, which is this, this. Um, Another one is this, this, and this. So we do not have this one, that's not available, because no, that one is also available because it's a part of 5. But we do not have this one available. So out of all these, like you can see, we have all these available. Uh, 2 and 0 edge is not available because that's already a part of MST, and 2 and 5 is already a part of MST. So in this case, we'll see what is the minimum edge. We have like 3 and 5. That's the minimum one. Now, since 3 and 5 are not in V, we can pick that edge and we can move 3 here and 3 out of this V minus S set. So in this case, now we'll have 3 edges, which is 0 to 2, 2 to 5, and 5 to 3 as a part of our MST algorithm or the MST output. Next, we have now 4 vertices that are connected, and we have to see, like, based on our cut, what are the edges that connect these 4 vertices to the left side, which is 1 and 4. So in this case, we are going to first see what are the potential edges. So we have all of them now almost connected except this one, because 1 and 4 are still not in are still not in the V part or the V set. So we have, these are the options that are available. Now, we discussed the fact that we have to find out which of the vertices connect this V to V minus S. So in this case, all the vertices that are in this set, like if there are edges that are formed between 0, 1, 0, 3, 0, 5, or 2, 0, 2, 3, 2, 5, something like that, they should not be counted, because otherwise we'll have a cycle in the graph. So in this case, you can see that although we have like these many options, we cannot connect 0. Like if you see the minimum one out of all these, the minimum one is going to be like we have several choices, which is one is this, because it's 5. This is also there, this is also there, and this is also there. But 0, 3 is already there in this vertex set. So we cannot choose 0, 3 because it will form a cycle. Like it doesn't make sense because it will form like this entire cycle. Another one is 4, 5. So 4, 5 is a possibility. Yes, we can choose that. But if we see 2, 3, like although it has the value 5, 2 and 3 are both in vertex V, like they are here. So we cannot choose 2 and 3 because they have to connect, the edge has to connect V and V minus S. So finally, we have two options, 1 and 2 and 4 and 5, uh, that are available to us. You can pick any of them. So let's say arbitrarily we pick like 4, 5 instead of 1, 2. This should be like 1 and 2. So if we pick 4, 5, now we are going to move the 4 from this set to here, and we'll have just one that is available in V minus S. So next, our cut will look something like this, which is 1 is on this side and everything else there. So again, we are going to see what are our potential things that are available, what are our potential edges that are available. We just have 3 potential edges that are available in this case, because everything else, like although we have 2, 4 here as well, but 2 and 4 again are already in this V set. So there should be some connection between V and V minus S. So in this case, we are going to pick like 1 and 4 and move the 1 to this set V minus S, to the set V. So we pick 1, 4, and this will give us, like, since V minus S is empty now, the minimum spanning tree will look something like this, which is we have all these different edges and each of them are traversed just once per set of vertex. So the total sum of the minimum spanning tree in this case, it's going to be 15, because we have like 3 and 5, 8, 10, 14, and 15. Okay. So the algorithm for Prim's algorithm is shown here. So it's exactly how we computed, which is we take into input an undirected graph, which is connected and also weighted, and we output a minimum spanning tree. That's called T, or the sum of minimum spanning tree. So initially T is going to be empty, and we pick any vertex in G and add it to T. So T is acting as our S set. So for every edge, that is for J equal to 1 to n minus 1, so for every vertex in G, or in V minus S, what we are going to do is we are going to see if the endpoint, like if C is the set of edges with one endpoint inside T and one outside T, then we are going to, so basically what we are trying to find is if each edge has one endpoint in S and the other one in V minus S, then we add e to the minimum weight edge in C, and we also add e to T, which is we are now moving the vertex endpoint from V minus S to V. So the overall complexity for this code is going to be O of EV, because um, we are computing it for all edges, like we are considering all the edges, and for every vertex, like we are running this loop V minus S times, because we have V minus S, the number of elements in set V minus S is going to be V minus 1, which is we have one source vertex in the set V and all the other vertices in V minus S. So you can reduce the complexity of this algorithm to O of E log V using priority queues. We are not going to cover like how to use priority queues to compute prims, but if you're interested, just check out the code on the internet. But we can also talk about this in one of the problem solving lectures. So that's pretty much it for Prim's algorithm. What you're supposed to do for the exams is you need to know like how to compute the minimum spanning tree in case of a graph for using Prim's algorithm. Also, you might be required to understand like how to write pseudocode for Prim's algorithm. You do not need to memorize the complexities. It's generally not asked. But we are going to now discuss the next algorithm, which is the Kruskal's algorithm, in the next video.